Welcome friends, in this video I'm going to show you using a simple roof, so to speak, how to understand the concept of a partial derivative. You'll see this is nothing fancy. I'm going to zoom in here a tiny amount more. As you can see, that pretty much looks like a surface in 3 dimensions, you see? And now look, down below there, that is the positive x-axis. Going up and down is what we call the z-axis. And then going over there, out of the corner up to here, that's the positive y-axis. So I have a 3D coordinate system set up, a kind of grid. And then from this perspective, you see that, for example, a graph like this pretty much is a roof, and that's it. You can imagine standing under it right there, for example, at some point in the xy coordinate plane. That there on the bottom is the xy coordinate plane because this is the x-axis, that there is the y-axis. So this entire plane where the focus is would be the xy coordinate plane. That's it. At least a portion of it. Let's take a look at the concept of slope in 3 dimensions. In calculus, we use a lot of fancy schmancy language, often kind of conceals the simplicity of a concept. When I look at this, if you look at it kind of, carefully and allow for the fact that it's basically a paper model and not necessarily 100% perfect at every tiny detail, when I trace this way, you see that, for example, I'm going to do it without my pointer. It keeps coming off. I need to fix that. This is stuff I have to make by hand, so look, when I trace this way, you see I'm keeping the same z value the entire time. And what I mean by the z value is, look, in the corner over there, that z value, I'm going to zoom in on that right there. See that? That is a 5 right there. So when I trace along this, that's a z constant value of 5 the entire time, over to here. So we experience that as a flat surface in 3 dimensions. What I mean by flat surface, I mean specifically level surface, meaning that you're not going up or down. You're traveling along a horizontal surface the way you see here. That means the slope is 0. Now let's change the slope a couple different ways and illustrate some other possibilities. I'm going to do that now. Here the slope clearly is different. I'm going to zoom out a tiny amount and maybe change the view just a little bit. So take a look. How do we calculate the slope? Well, the slope is calculated as follows. Take a look. Begin over there at 5. In this position where I'm pointing, I'm going to count 1, 2, 3, 4, 5, 6. So I counted 6 along the x-axis, and then I'm going to count 1, 2, 3, 4 along the z-axis. So I'm going to count again 1, 2, 3, 4, 5, 6 along the x, and then 1, 2, 3, 4 along the z. So clearly, the way you look at it from even your perspective, you can see that this is a sloping surface now. It's still a plane, because when you look at it, take a look, right? It's still a plane because it's still flat. It's still a plane. But it's a tilted plane this time. Tilt is what we call the slope along the x-axis in this case. And this is a positive slope. So it's positive in the following sense. Slope is calculated as the change in the vertical over the change in the horizontal. So here, take a look. The change in the vertical, beginning from z equals 5 right here where I'm pointing. I'm going to do it this way. You can see better. Look, it's 1, 2, 3, 4, 5, 6 this way, and then 4 up. So the 4 divided by the 6 is the slope. That's all. So before I put this away, I'm going to take this, and I'm going to place this triangle over here. Take a look so you kind of emphasize the point. You see that? It's what often we call a basic slope triangle, as you see, right in this position. And it tells you the slope. That's all. You can count. How many for example, along the x-axis, and then how many up, and that's it. So that's one kind of slope. Let's change this a little bit. What I mean by that is I'm going to give this a negative slope now. Take a look. That there, as you can see, is clearly a negative slope. And negative means, look, I'm going to put this thing over here, and look, it's going to roll. You see that? It rolled. So you would experience that, for example, as a surface that you can slide down on. Shoot. So let's count it. I'm going to count 1, 2, 3, 4, 5, 6 along the x-axis, and then 1, 2, 3, 4 straight down along the z-axis. So this slope, you would say, is negative 4/6. It's the change in the vertical divided by the change in the horizontal. The horizontal is a positive, but the change in the vertical clearly is negative. You're falling from here. Where I'm located, you're falling. So that's negative 4. So negative 4/6 would be the slope, and you can illustrate it this way. Take a look here. I'm going to put this like this. Take a look as shown. And that there is illustrating the fact that it's a negative slope. So I've told you about the slope in X direction only using a simple plane. That's a good place to begin. You can really understand that as a simple roof, and that's it basically, that you can kind of, angle in different ways. I'm going to take this away, and notice that this slope in fancy schmancy calculus language, this quantity would be measured basically as the slope with respect to the x-axis right here, because this is the x-axis, and you're measuring the slope in this xz plane. This plane right here, where I'm kind of moving my pointer, that's the xz plane. So that slope would be measuring, for example, how does z change as you change x? So specifically to emphasize that point, when I answer that question, I mean every time x goes up, for example, by 6, the z goes down by 4. That is what we mean by a rate of change in this xz plane. That's it for this one. In another video, I'll do something similar, but I'll explain it from the other perspective of the zy plane. Thanks so much. Please leave a like and subscribe, and I'll see you in another physical math video.